Okay, so now we're continuing on. We did our permutation testing, but we saw that there was a whole lot of, quote unquote, significant results or super threshold results that we got when we set the p-value to be 0.05. And I mentioned that p 0.05 is, it's a little bit too, well, not a little bit, it is too lenient because we are not correcting for multiple comparisons. And in particular, I'm referring to the multiple comparisons over all these time frequency points because we are doing a t-test or some kind of statistical test at every single time frequency point. And now we threshold them all at 0.05, so that's not really appropriate. And we might, for example, in this map, we might look at something like this and we think, well, maybe this is an alpha error. So we have a huge multiple comparisons problem. So maybe you think, well, I remember in my psychology statistics class that we learned about Bonferroni correction. And how does the Bonferroni correction work? Bonferroni correction is you take the p-value and you divide by the number of tests. So you might think, well, maybe we should do that. We just take the p-value, 0.05, and divide by the number of time frequency pixels that we are testing. So that turns out to be a bit insane, I believe is the technical term. So here, imagine we have in this plot 2,500 time points and 30 frequencies. So that gives us 75,000 tests. So that means our Bonferroni corrected p-value corresponding to 0.05 would be this number, which is very, very small. There's a few problems with this method of multiple comparisons correction. Well, I should be clear, there's nothing wrong with Bonferroni correction. It's a great correction for multiple comparisons. It's not a great correction method in this particular situation where we are doing a lot of tests over time frequency space. So you can try and think about what are some of the reasons why Bonferroni might not be very appropriate in this situation. There are three problems with Bonferroni correction for time frequency analyses. One is it's too stringent. You can see even with such a ludicrously tiny p-value, even true effects that are, fairly robust, statistically strong, are still not going to survive this threshold. So it's too stringent for sort of reality. But more importantly, it's Bonferroni correction assumes independence of all the tests, which we know is not true. All these time frequency points are not independent of each other. They are, in fact, highly dependent on each other. And even more important than this is Bonferroni correction is based purely on the number of tests, not on the information that's available in the results. And this is really the killer for Bonferroni correction in this in the context of time frequency analyses. So it's based on the number of tests, not on the information that's in the result. This is the reason why this is a problem is that the number of time points we have here is kind of arbitrary. So we could, so if you wanted to chop off a 0 from this p-value, we could downsample this a little bit to have 250 time points. Then all of a sudden we'd have a more lenient threshold, which doesn't make sense intuitively because the data or the results aren't really changing. The patterns in the results aren't really changing. We're just having fewer time points. Conversely, if you really wanted to get no significant results, you could upsample this map by a factor of 100, and then you would have you'd have thousands of time points, tens of thousands of time points, and the p-value would go down by orders of magnitude, even though the results haven't changed at all. You haven't changed this blue blob, these blue blobs here. Nothing has changed, but by making these really arbitrary decisions about how many frequencies you want to have between 2 hertz and 30 hertz or whatever, then that changes the p-value even though it doesn't change the content of the result. So this is really what makes Bonferroni correction or the Bonferroni procedure inappropriate for time frequency analyses. And just, at the risk of being a bit redundant, there's nothing wrong with Bonferroni correction in general, and Bonferroni correction certainly has its place in neuroscience. But for statistically thresholding time frequency maps like this, or space maps, or something where you have a lot of different points with very strongly correlated data, Bonferroni correction is really just not appropriate. So we can think of alternative methods. Maybe we think of something like a cluster correction. So we say that some super threshold region is meaningful. We want to interpret it if it's in a cluster, and a cluster would be like a region of contiguously significant pixels. So here we would call this 3 clusters, 1, 2, 3. So that's kind of intuitively attractive. Then you get to the problem of how exactly do you find a cluster? Is it the number of time points? So a cluster has to be at least, 150 milliseconds long. But how do you get to 150? Maybe why not 155 milliseconds or 143 milliseconds long? Or is it based on the number of frequency points? But then how do you pick? Should it span 4 hertz units, so like 10 to 14 hertz, for example? But that, you can see where this is going. These are arbitrary and poor choices. We want to have a situation where we minimize the arbitrariness of these statistical thresholds to the point where the only thing that's kind of arbitrary that we're selecting is the p-value, which would be 0.05 or 0.01. Okay. So the solution, you probably will not be very surprised to hear after the previous lecture, is to figure out an appropriate cluster threshold based on the cluster sizes that we would expect under the null hypothesis. Okay, so how does that work? Here is a time frequency map from the permutation testing. So here's where we shuffle all the condition labels, or in the data set that we worked on with the previous lecture, and we'll continue on with this lecture. These were comparing 2 different channels from 2 different electrodes recorded from the mouse visual cortex. So here, this looks sort of noisy, which is not surprising. This is the null hypothesis map. This is one of the maps that was created during permutation testing as a time by frequency plot. And it's thresholded. And actually, because this is a permuted map, we don't expect anything to be significant, right? This is the situation under the null hypothesis that we created in our data. So in fact, we would expect nothing to survive the thresholding. But the fact that things do survive thresholding means we consider these to be alpha errors. So these would be like incorrect little things. So we say each one of these things, these are the sizes of the results that we can expect under the null hypothesis at p less than 0.05. So now what we do is, from the first iteration, we find in this entire space, we find the biggest cluster. So this one is the biggest cluster. It has the most number of contiguously significant pixels. And then we go to the second iteration, we find the biggest cluster. The nth iteration, we find the biggest cluster. And now we build a distribution of the largest cluster sizes that are expected under the null hypothesis. So you see most of them are fairly small, which is, we expect that, right? We get null hypothesis is just random noise, basically, or random data. So we expect all these clusters to be very small. And of course, some tend to be big. This one looks pretty big to me. And now we can define a threshold cutoff, so we can say 95% of this distribution. And then we look in our real data, and if we see that there are clusters that are bigger than this threshold, we'd say they're unlikely to be present if the null hypothesis were true. Of course, you can already see in this plot, it can happen that, under the null hypothesis, you still happen to get a big cluster. But, this is how probability and statistics work. So here's how we pick our threshold. So before going on, I'll just say there are multiple ways of defining these clusters. So I was talking about the size, just basically counting the number of pixels in each cluster. But you can also do like a weighted count, so you can weight them by the magnitude. So let's say like the t-value in here. So then you would say, so for example, you could take the sum of all the t-values in this cluster, and then you would want to do absolute values, so the sum of all the absolute values in a cluster, and then you take the largest one. That one is actually nice, taking the sum of all the t-values in each cluster, because now you're not only selecting for really large clusters, you're also selecting for smaller clusters that are really, really significant. So, but anyway, there's a couple different ways you can do it. The simplest way is just to count the number of superthreshold pixels. I think this is what we do in Matlab in a few minutes. So then you get a map like this, and then you would say all the small clusters, all the clusters that are smaller than this threshold, we set those to 0. We say those are not significant. So here is the same map with this previous data, and you can see after cluster correction, this little guy, if you remember, there was a tiny little cluster here, and that disappeared. That disappeared because these two clusters were larger than this threshold, and that small cluster was had fewer pixels than this threshold. So that is one solution for doing multiple comparisons correction. Another solution, and I'll show you both of these solutions in Matlab in a few minutes. Another solution is to find the maximum, I say here t-value, but this would be whatever your statistic value is during the permutation testing. Find the most extreme value from the null hypothesis map. So now we're not talking about clusters at all, we're only talking about the distribution of individual pixels. So the way that works is here, this is now a very similar map to what I showed 2 slides or 3 slides earlier or whatever, except now this is not threshold, and now we just take the 2 largest extreme values. So we want the largest positive value and the largest negative value. So this would be from the first iteration of permutation testing, the second, the nth iteration in permutation testing. And now our distribution will look something like this. So it's going to be bimodal, because from each map, from each iteration, we take the smallest, or I guess I should say the largest negative value and the largest positive value. So that gives us these distributions. And now our threshold is going to be based on the edges of these 2 distributions. So here I'm drawing this as a, so this would be like a 2-tailed test, right? So we have half the tail on this side and half the tail on this side. And now we threshold the actual time frequency map according to these thresholds here. So now you can see the results look quite, well, not quite different, but a bit different. So 2 noticeable things. One is that this got a bit smaller. This feature down here got a bit smaller. And you can also see that we have some really tiny clusters here. In fact, I think this is really, these are just individual pixels that get stretched out a bit. So that can, that happens. Whether this makes sense and whether you want to allow these sorts of very small findings into your data, I think really just depends on your assumptions about what's happening in the brain and in this task or whatever. If you think that there might be some highly significant and meaningful and interpretable, theoretically relevant findings that are very short or very fast and localized in frequency, then this approach might make sense, and maybe these little guys are interpretable. In general, this method, this extreme value method, max pixel thresholding, tends to be more stringent than cluster-based thresholding. So now I'll go back a few slides so you can keep this map in your working memory for a bit, and now we go back and compare that to this one. Same data, just thresholded using cluster-based correction or max voxel-based correction. So I think, let's see, we'll skip that. So now we can look at this in Matlab. So now this is the same script as from the previous lecture. And the same figures are open, in fact. So this is the thresholded map of the threshold map, but not corrected for multiple comparisons. That's what I meant to say. Okay, so let's see what's going to happen here. So here I define a vector of max cluster sizes, and it's going to be a vector based on the number of permutations, which is 1,000. So this is going to be where we store all of the maximum cluster sizes under the null hypothesis. Here's where I store the maximum values at each pixel, so it's going to be the number of permutations by 2. 2 is for the smallest value, or the largest negative value, and the largest positive value. Now we loop through permutations. This matrix permaps, this is what we created earlier. So if you remember from the previous video, well, if you don't remember, then you should go back to the previous video and watch that one. Now here with threshold, this is a little bit unusual, right? So we're thresholding the permutation map. So again, this is where we expect nothing to be significant. But of course, in practice, there are things significant because we're just using a p-value of 0.05. And we're not correcting for multiple comparisons, so of course we are going to get some alpha errors here. Then I use this function bwconcomp, which is in the image processing toolbox. So yeah, well, if you don't have the image processing toolbox, then you'll have to, yeah, I think there are other solutions for this, but well, I'll have to look that up. So let's see. So that's going to generate a variable called our structure called islands, which is going to contain a list of all of the objects, all the contiguous regions, all the clusters in the map. And now I get the lengths of all of those using this self-fun function. So I'm going to get the length of all of the lists of pixels in each map, and then I just take the biggest one. So that we do for all of the islands in the null hypothesis permutation map, and then here I get the extreme values, and in fact here we don't really need to sort them. I think I was doing this for some other reason, but anyway, so here I happen to sort them for whatever reason. But this is the important point, that we take the smallest value, the minimum value, and the maximum value. Okay, so this goes in a loop over all of our permutations. And now this is just showing a histogram of the cluster sizes expected under the null hypothesis. So you can see they're mostly clustered at relatively smaller clusters, although they don't go down to 0. And in fact, often they don't, right? It depends on the smoothing characteristics of the data. The more smooth the time frequency map is, the less likely you're going to find clusters that are way down here, like 1 or 0. I forgot to mention this during the slides, but let me go back very briefly to this thing. So now, this is, I said that Bonferroni correction is inappropriate here, mainly for this third reason, that we have an arbitrary number of time points and an arbitrary number of frequencies. So this is why cluster correction is appropriate in this situation, because if we were to upsample these data by like a factor of 1 million, so we would have like several million, like 10 million data points over here. These clusters are going to be huge. Each of these clusters will be, hundreds of thousands of points big. But in the real data, the actual clusters will also be scaled up to exactly the same size. So that's what I meant by the the cluster correction and maximum pixel correction, these are based on the information that's available in the results and not just the number of tests that you're doing. Okay, so let's see, and now I'm going to make some plots. Now this is the same plot as this one. This is without doing any multiple comparisons correction, and here we apply cluster-based correction. So here's the raw map. You can see that's really exactly the same. This is the same raw map, but with contours drawn around. So you can see, well, it's a little bit difficult to see these contours, but you could change the color scaling if you want. But you can see it's quite a difference from this previous one. And here's the thresholded one. So now you can see we really just get two regions of significance here, this early lower frequency difference and this later gamma band difference. So this is with cluster-based correction, and now with maximum pixel-based correction. And now, so this is also interesting. So now this is the same three maps. So it's interesting to compare figure 2 and, well, okay, figure 2 is actually not that interesting, but it is interesting to compare figure 4 and figure 5. Of course, a lot of these differences are the same. So this thing and this thing, that's the same in both. But one thing that's different is this cluster is significant for maximum pixel base, but it's not significant for cluster-based correction. And so what's happening here is that this is a very small cluster, but it's very strongly significant between the two. And so when we just base our clusters on, you know, these kinds of results, basically these really big sort of spread out results are biasing our statistical threshold to select only for, to reveal only clusters that are really large. So we lose this additional one. And this one also seems to pop out. So yeah, so I guess that was, I think that's it. So now you see these two methods for cluster-based, for multiple comparisons, correction of time frequency analyses. One final point that I wanted to make about showing results. In general, I'd recommend to show all of the results and then to also show the threshold. So something like, you know, I prefer this method. In this particular case, this contour is difficult to see. So you need to adjust the color scaling or make the contour lines darker or thicker, I mean. But in general, I think that's better. If you only show the supra-threshold results, I think you get quite a different picture of what's really happening in the data. So you can see here's this big feature that's almost significant. Maybe that's relevant for some other experiment or some other kind of theory or idea, and you just don't see that here. And here's an example with real data. I think it's pretty clear that this time frequency map shows a lot more of the results. You can really interpret this map a lot better, and you also see what is statistically significant. Whereas here, you know, in this plot, you just you zero out all the non-significant pixels, and you don't even see that there is this big beta band suppression up here. So, well, I'll let you be the judge of which is better to show. My personal recommendation is to do something more like this rather than something like this. Okay, that's it. I hope you found that lecture instructive, and see you in the next lecture.